All right, we'll do this. We'll do this review by way of random name calling. Are you ready? John, give me anything you know. Anything at all about this guy on the board here, R of X.
All of it?
No, just one thing. Save something for someone else.
The asymptotes is 5. X equals 5.
Okay, which asymptotes? And what are you talking about?
One of the vertical asymptotes.
There's a vertical asymptote? Okay, and how'd you get that? X equals 5, a vertical.
The set at the bottom, the denominator equals 0.
Okay, okay.
Oh, and then factor and solve.
All right, so how does the denominator factor?
The quantity of x minus 5 times the quantity of x plus 4.
All right, so do you want to give us the other vertical asymptote as well while you're at it?
It's also x equals minus 4.
All right, so does that ring a bell? Okay, we get these discontinuities on this function clearly just from the form of the function. You know something's going a little weird with those two values because if you plug them in, this thing misbehaves, right? What else do you know? How about give me some other piece of information? Alex, what you got? Anything at all?
The Y-intercept is 3 over 10.
The Y-intercept. How do you get that?
I just put 0 in for all the x values.
Right. It's the way you. There's nothing special about finding the Y-intercept for a rational function. It's the same way you find it for any function. Plug 0 in. Yeah, exactly. Caden, give me something else. You know, if you could say something else.
The horizontal asymptote is 1.
Okay, so there's horizontal asymptote. And let's get in the habit of giving the equation of those asymptotes.
Y equals 1.
Yes, y equals 1, because an asymptote, as an object, an asymptote is a line. So good. And how you want to say a little bit about how you reason that, or what's the deal? What's
Top and bottom. I learned
thanks,
like
guys, back over.
top heavy, bottom heavy, equal heavy.
Equal heavy.
Like,
Okay.
Yeah, like the coefficients of the highest degree, you divide them if they have the same degree on the top and the bottom. So
Okay.
it's over 1.
Yeah, it's kind of like tie, kind of. All right. Yeah, so we'll say some more about that in a minute as we start some of this discussion. And then what are we missing? What are we missing? And do it and find it if you can. Let's see it.
The x-intercepts.
And how do we get them? And how did you get those?
If you factor the numerator, you get x plus 3 and x minus 2.
Like that. And the only way that this overall fraction could be 0 is by making the numerator 0. I got you. Okay. All right. So is this good? Have you taken just now a trip down memory lane? Hopefully, this is stuff that was talked a little bit about in your algebra course. But you know, and besides reviewing, so some of our goals today, we'd like to be able to graph something like this without the use of a calculator to somewhat degree of accuracy, get a real good feel for what it looks like. And we're also going to throw one more wrench in the works. We're going to introduce something called a slant asymptote to you today. All right, but before we do any of that, I know it's exciting. Was that like a good? That was some good excitement there. Before we get involved in this too much, we should say what a rational function even is. We've been messing around with one already, and we haven't even told you what one is. Well, here's the simple definition. It's a polynomial divided by another polynomial, right? And actually other things that we might look at obey some of the rules that we'll talk about today. But if we're thinking of strict, what is a rational function, then this is technically the definition. And I like that definition a little bit. First of all, why is rational a good name for these kinds of functions? Say it, Tim. Because they're fractions, right? I mean, they're not fractions, but they're rational. I mean, they remind us of fractions, though, right? They're a ratio of two polynomials, right? And this kind of is a nice. This is beautiful, right? Because we've been making this. Building these two towers in our lives. We've got numbers and polynomials in these two towers. And we've seen these beautiful parallels between them. Factorization, for instance, the fundamental theorem of arithmetic I told you about is in like the number tower, and the fundamental theorem of algebra is in the polynomial tower. And there are these nice properties of both. You know, over here in the number tower, we have that an integer plus an integer is another integer. Over here in the polynomial tower, we have like a polynomial plus another polynomial is another polynomial, right? There's like this sense of closure to any two things when you add them give you another same thing of that same type. And then the factorization theorems, which are really important. Any integer has a unique factorization. Any polynomial has a unique factorization. There's these nice analogs between them. So this is a nice analog as well. So we have rational numbers, and we have rational functions, right? And if we were to put those in two towers as well. Yeah?
What is a monomial? How does a polynomial?
Sure, yeah. All right, so let's consider, before we do too much else, the very simplest of all rational functions, 1 over x. There it is. It's beautiful. I'm holding it up again on this card. This is the one we met the first week of school, I think, is even when we started thinking about him again. And it's the one that, you know, we all know and love really well. So, with that in mind, how do we transform our good friend? Take this and tell me what to do to it, please, to get a graph of A, or then B, and then C. And I'm going to call on some random people here in a second. Give you a second to think about them. But I've done some kind of series of graphical transformations to produce this new graph. What have I done? Lizzie, you want to take a stab at the first one? Go ahead.
So it's upside down because it's negative, and then it's moved up by 1 unit.
Okay, I think I like what you said. I'm going to ask you, I'm going to push you on the precision again. By upside down, what do you mean?
Reflected plus the x.
Okay, yeah, so reflected. So start with 1 over x, reflect it over the x-axis, and move up 1 unit, and you'll get this picture. All right, so this is a good review of things we thought about before. Do you agree with Lisa? Anyone disagree? Anyone want to pick a fight? Okay. No? All right. Apparently she's right then. All right. Rachel, you want to help us out with the next one when you're ready? What do you think? What do we do? Rachel, Lisa. Yeah. What do I do to this picture to get the picture for B? Left 1 unit and like call it a day, right? All right, there you go. And then what about this next one? What does it say? Cam. What do you think on this one? What's going on in C?
Is it left 3?
Okay, left 3. Anything else you want to say? What about that 2? What does that do?
This is the one I never understood. So
I know. Haunting you. I know, it's exciting that you got it actually. Yeah. Face down the demon. Go ahead. Stare at that.
Is it stretch?
Oh, what kind of stretch? By how much?
2?
By which direction though?
Horizontal?
It's a vertical. It's a vertical stretch. Yeah, that's correct. Vertical stretch. Wait, what? Help us out here, because I'm struggling with this too. This is rough for all of you. I know it's not you. You think? I think it's I think I need someone who can like not just think but justify too here, right? What do you say, Peter? Okay, can you justify why? I mean, what makes you say that? Because people are having trouble and they're like, okay, I believe you, maybe, right? Like maybe you're right, but they don't know why. Like I want to make sure everyone's like clear on why that's definitely you're right. You actually are. I'll just come out and say it.
Because if it was a 1, then if you plugged in 1 for x, it would make 1 for it.
Okay, so by way of example, you're showing that it's like doubling the y values.
It's
Okay.
like the the numbers on the y-axis are right.
Yeah. Go ahead, Eric. Say something else.
Because 2 over x plus 3 is just 1 over x plus 3 times 1 over x plus 3 times 2. So
Yeah.
like there's multiplying the entire thing by 2.
Yeah. This is like if let's forget about the plus 3 for a second. What's 1 over x? That's our original function. What's 2 times 1 over x? Isn't that 2 over x?
Yeah.
And isn't that clearly a vertical stretch by definition?
And those horizontal, then you multiplying the x by x.
Yeah. All right. Now, actually, I want to highlight something just for fun here. Could this be thought of as a horizontal something or other too? Like, how can I could I bring this 2 into the picture down below too? Maybe I could. I don't want to kill you with this. I mean, this is fine. We can just move on if you want, but I just love this stuff, right? So go ahead.
This isn't actually an answer.
All right.
How
Okay.
would you distinguish between a vertical string and a
It depends on the function, right? Like, so if you have like some polynomial, say, that's crossing the x-axis at all these different places, a vertical stretch means something very particular about it, right? We're moving it up and down, or a vertical shrink. We're moving it up and down, and all the zeros don't change. Not at all, like at all, true of a horizontal stretch or shrink, right? Do you agree?
Yeah.
So, in fact, there's no general reason why those it's never, like you can't be like, well, all I need in life are vertical things. Like sometimes you need a horizontal thing, you know.
In the specific
In this specific
example.
example?
Yeah,
Okay.
it would get set to the denominator.
Okay, so what am I gonna write down here?
Like if it was like a vertical stretch of like a full string of 2, it'd be like 2x plus 6, I guess.
Yeah, which would that be? That'd be a shrink, wouldn't it?
Yeah.
Okay. Yeah. It'd be a horizontal shrink by a factor of 2.
But that was originally a vertical stretch.
Or it could be a vertical. It's either a vertical shrink or a horizontal shrink by the same thing. Yeah.
So they're the same.
Maybe for this one they are. Yeah. Right. And that's what I'm about to say here too. How would you rewrite this? 1 over. This is also 1 over x over 2, isn't it? Aren't those the same thing? So this is saying again what Lucia just said. This is either thought of as a vertical stretch by a factor of 2, or a horizontal stretch by a factor of 2. Yeah. For this, they happen to be the same, which is like a little bit mind-blowing, right? But in general, please don't get the impression that in general this is always true. Like this is actually amazing if that's true here. The fact that we stretch it vertically by a factor of 2 or horizontally, we get the same picture. What? Like that's really hard to wrap your mind around, actually. It actually kind of reminds me of part A too. What could you have said instead of reflect over x-axis up here? Forget the plus 1. What else could you have said instead? What is negative 1 over x? Reflect over x-axis. But you could have also said what?
A reflection of the y-axis.
A reflection over the y-axis. You get the same picture whether you reflect this over the x-axis or the y-axis, don't you? So full credit for either one there. All right, so I'm just trying to mess with you. That's mainly what I'm doing. Okay. All right, for D, this is going to mess with you a little bit too because I'm like thinking, wait, is that even a transformation of 1 over x, Mr. Chase? Doesn't seem like it to me. I'm not ready to answer this. Well, before we answer this, just let's ask kind of a fun question on the side, just for fun. Okay? Are you ready for a fun question? I'm just curious, just because I'm like a curious guy, I'm curious to do this following division problem. I've been doing division recently, and I love it. Okay? I'm just thinking I'd like to do this problem just for fun. X goes into 3x 3 times 3x. I love this. This is gonna be done in a second. This is my favorite. Why didn't you give this one to me on the quiz? I would have been prepared for that.
Yeah, can you please give us that one next time?
What do we get down here? A negative 1. Okay, so one way in particular that you could report your answer to this is the following, right? This is going to be kind of an interesting idea because what we said is one way to do this is in like fraction form, right? It's actually the way that you came into this class being like in love with from elementary school. What is this divided by this? The answer is quotient plus remainder over divisor. And then stop and step away from this for a second.
Oh!
Step away from this for a second and realize what you've just done. Like you're reporting division. Reporting division is what you're doing, but you're also like writing this original function in another completely equivalent form, aren't you? And if you don't believe that that's equivalent, then just find a common denominator. Multiply 3 by x minus 2 over x minus 2 and add them back together and see that in fact this is no different than what we started with. All right, but we like this maybe a little better because we can finally answer the question. This is a transformation of 1 over x? Yeah, maybe it is. What do you want to say, Peter?
How does that work? I don't know. I just can't get my head around how could we remainder over divisor?
Yeah, so it's just like if someone said, like, what is, I think the example I used the other day is, what's 22 divided by 7? Someone might say, what would you say? You'd say 3, right?
Yeah.
Plus 1 over 7. Right?
So you're saying we should have taken algebra 2 back when we were in 3rd grade?
Yeah, I mean, algebra, yeah, this is the same result exactly, right? You'd say 3 and 1/7, but like when you're doing mixed fractions, like back in the day, someone should have told you that by 3 and 1/7 you mean 3 plus 1/7, right? That's exactly what you mean. Okay, I'm ready for someone to tell me what transformations occur here. Could someone do that for me? There are 3. Name them. Go. Someone. There's 3 things. You want this? Go.
Is it reflected over the x-axis?
Okay, reflect.
Or y-axis.
Or y.
Reflect on axis.
One of the axes.
Yeah, choose an axis. Not both though, but okay, keep going.
Oh, still me?
Yeah,
Okay.
still you.
Right
Go all the way.
to-
Right 2. And
Up 3.
up 3. Okay, so that's easier in that form, I think, to see that. Another thought, question from someone? I'm done talking about transformations then. If you're not.
What order are you supposed to
Yeah, this is always like an issue, right? I would just stick with stretches and shrinks first, or reflections, and then movements, translations. Yeah,
Go up 3 and then reflect it.
but that's a complicated question. Yeah, so let's be clear. I'm starting with the function 1 over x. Start with the function 1 over x. Go. Reflect that over the x-axis. What now? What do we have now? Or negative. I'm going to say negative 1 over x. Yeah, because I said reflect over the x-axis. And then, what does it mean to move something right to? You take the whole function, and anywhere you see an x, you replace it with an x minus 2. Right? So right now we have negative 1 over x. Replace x by x minus 2. Is that okay? And then add 3. Right? So that's my thought process. I'm thinking, okay, I know what 1 over x looks like. I know what that looks like. Replace x by x minus 2. And then move up 3. Yeah, Rose.
If the order of transformations, if you had both a reflection,
Okay, guys.
if you had both a reflection and like a strength,
It actually doesn't matter because one only affects x coordinates and one only affects y coordinates. Yeah. All right. So don't dwell too much on the transformations. That's actually not the big idea today. All right. Here's our rational function that we're interested in, right? E f over g. Okay.
Why do you do this to us?
And by polynomial divided by polynomial, I mean, thanks guys. I mean this crazy notation with triple dots that I referred to on the first day when we were doing polynomials, right? And I know this seems like crazy to write that out, but I need to put up these like properties in boxes, and I need to refer to things like n and m and have you know what I mean. Like for instance, what is n and m in this notation up here? The number place.
Is the power of that?
It's the power.
Like the degree.
It's the degree. I like the fact that precision is like coming to us right now.
It's also the number that's
It's the degree of, n is the degree of the
First term. The highest term.
it's the degree of the whole polynomial, right? So n is the degree of the numerator, and m is the degree of the denominator, isn't it? Using my notation up here. Is that okay? I'm just reading it off here. N is the degree of the numerator, and m is the degree of the denominator. All right, so now that we have that firmly in mind, now we can say if n is less than m, and by that we mean if the degree on the numerator is less than the degree in the denominator. But it's easier to say if n is less than n. Then we have a horizontal asymptote of y equals 0. And I know you know these first two because like you demonstrated in the warm-up today that you do. So if n is less than m, we have a horizontal asymptote y equals 0. That is if we have like 2x minus 1 over, I don't know, x squared minus 5 or something. Then we have a horizontal asymptote y equals 0. Why? Can someone justify that besides just like mathematical magic? Someone told me once arbitrarily, my teacher, I trusted them. And can someone tell me why it's y equals 0? Like, why does that make sense? Justify. Yeah. Okay, okay. No. I kind of feel where you're going with that. Okay, but you don't want to add to that? What do you think? I don't know. Why is it y equals 0? I'm still curious. And then this is the case that Caden and I were talking about during the warm-up, right? If n is equal to m, if that is that the degree in the numerator and the denominator are equal, then we have a horizontal asymptote that is equal to y equals the ratio of these two coefficients, an and bm. Right? That is if we have like 2x squared minus 1 over x squared minus 5.
But we don't.
If we had that, then we'd have a horizontal asymptote of y equals 2 over 1. Right? Or y equals 2. Why? But again, in both cases, why? I still haven't heard anyone give me an explanation for why the first one here has an asymptote of y equals 0. Why is that? Yeah, no?
Because I guess you're sort of creating a fraction and that's always less than the total statement of y equals 0.
It'll always be less than 1. I have to think hard about whether that's true or not.
Or it won't always, but if you have x over x squared, then it's like a fraction of that.
Okay, so that's kind of what Isabel was saying. This is you're thinking of it as if it's x over x squared, kind of. Let's go back to the definition of a horizontal asymptote. When do we get a horizontal asymptote? By definition, like day 1, properties of functions. What is an asymptote? What is a horizontal asymptote? Actually, you remember this? It was the limit as x approaches infinity or negative infinity, right? So can you bring that to bear here? What happens when x tends toward infinity is what I'm saying. F of x tends to what? I mean, what happens when you plug in numbers close to infinity? Yeah, I mean, we get something that's linear and something quadratic, and the quadratic thing will always be bigger, right? Out at infinity. Again, like plug in 1,000,000. We'll have like 2 million, basically. Who cares about the minus 1? It'll be basically 2 million over 1,000,000 squared, right? Like, who cares about the 2 million when you have 1,000,000 squared down the bottom? Keep in mind that by 1,000,000 squared, we mean like a 1 followed by 12 zeros, right? Okay, that's a lot. Okay. So the point is, this is very close to 0. 1,000,000 something. So it's approximately 1 over 1,000,000 is what it is if you plug in 1,000,000. Isn't that? Excuse me, 2 over 1,000,000, right? It's approximately 2 over 1,000,000 if you plug 1,000,000 in. Or is that enough to convince you that we think that as x tends toward infinity, not just 1,000,000? Because 1,000,000 is like nothing. Like we can get much bigger. Okay. That this tends to 0. That'll always happen if the degree on bottom is bigger. It's growing faster. And then same here. If you plug in 1,000,000 to here, can we use the same kind of logic as we go out to infinity for this guy? Yeah, we have basically 2 million over basically 1,000,000, right?
So that's 2.
Which is, yeah. If these -1 and -5s are negligible, right, then we basically have the function 2x squared over 2x squared, which is basically just the function. I mean, out at infinity, we have 2x squared over x squared, which is just the function 2, right, out at infinity. So it makes sense that it goes to just the ratio of the coefficients. Rachel? No, that's not him. Okay. All right, now the last one's a little bit crazy, the fact that you haven't probably talked too much about this. But we have, if the degree on top is greater or equal, if it's greater, then it's the quotient of those two things. And this is, like I said, the first time you'll ever talk about a slant asymptote. But if when we do the division, The slant asymptote is the quotient when you do the division. So, if it's linear, then we call it a slant asymptote. This will happen when the degree on top, a slant asymptote in particular, will happen when the degree on top is 1 greater than the degree on the bottom, okay? So you'll see. When we do one like that, you'll see. It'll be a wonderful experience, I know. All right, so that's we're going to call that, you notice we're talking about this as the end behavior asymptote because it's a horizontal asymptote, or maybe it's a slant asymptote. We're not going to call that a horizontal asymptote.
So what's the point of that equation?
Well, we're going to still use it right here, right? So we're on some of the other ones. We needed n and m, didn't we? And an and bm.
Well, we knew how to.
All right, these should be no surprise after our conversation when we came in, so I'll just put them all up here. Vertical asymptotes, you know where those happen when we have a 0 of the denominator. X-intercepts, zeros of the numerator. The Y-intercept for any function, and of course these two, is the value when x is 0. And then there's one thing I haven't put up here yet, and it has to do with the parenthetical comment that appears in number 2 and number 3. Do you see what it says in parentheses on those? As long as they aren't also zeros of the numerator, or here, as long as they're not also zeros of the denominator. So what happens when that occurs? It's a whole, right? So that's the other case when, if you have something that is a factor that appears both in the numerator and the denominator, then you get the appearance of a whole. Right? That part is review. Slant asymptote is going to be fun for us, I think. We'll like that.
Wait, does that mean that in a very, very, very weird rational function you could have an asymptote that is quadratic or something also?
Right, exactly. And actually your book goes into that, but I won't really stress anything more than just the slant asymptote. All right, I'm going to put the next problem on the next slide because some of you are still copying this and you're having fun. I'm going to put the next problem on the next slide over here. All right, and the next thing we're going to do, so you can start thinking about it, is I want to graph that, okay? I'd like to go full out without a calculator and graph that, okay? That's like the next thing we're going to do in our lives right now.
With our hands. Like using our hands.
Using just by hand, exactly, no calculator. So you can start working on it now if you like. I'll put the slide up in a minute with that on it. Too.
Wait, graph it, or do we have to show all?
Well, I think it'll help to do all the things, right? If we're going to graph it, it might be nice to do all the things first. Whatever all the things might need to do. Okay, can I get rid of this slide yet? I mean, remember you can always, like, it's online, it's on, I'm taking a video, and it's right, all this stuff. Okay, so.
Well, it's not a video, it's just
I mean, it's this.
what?
It's this. It records sound and this screen. Right now, yes, you and me. We're going to be live on YouTube tonight. All right, let's do this. So this is the function. It's actually b of x. Sorry, whatever. Okay. So talk to me. What do you want to do? And some of you already started thinking about this problem. So. Yeah, I mean, you have an irresistible urge to factor stuff, right? Don't you? Like, that should be innate. Okay. So, can you do that for me, please? Someone, go. Factor the numerator. Eric.
Oh, okay. X minus 2 and times x plus x minus 1.
Does that work for everyone else? Anyone have the denominator? Oh, it's so exciting. Everyone's so excited. Long way. Go ahead. X plus 2, x minus 2, what'd you say?
X minus 3.
X minus 3. How'd you do that?
I just did I'm not sure what it's called. It's just,
It's called factory by grouping. Yeah. That works. If you can imagine a case, right? If I was like creating a really excellent problem for you, where you might even have to like, I don't know, do the rational root theorem and think, right? You have to like maybe work hard to factor that, right? We could give you a problem like that. Okay, now.
So put points at.
So tell me what I need to do.
The point at 1, the point at 2.
All right, we got an x-intercept at 1. Let's write this stuff down. We got an x-intercept at x equals 1. What else we got?
1 at x equals 2.
At x equals 2, we have an x-intercept also?
Yeah.
It's a hole, right? Yeah, careful, right? X minus 2, x minus 2. There's a hole there at x equals 2. So that's it. What else? What else? Give me something else. Anything you know. Matt.
A hole at x equals 2.
Okay. Anything else?
At x equals 0. There's a point at 1, 0, 1, 6.
Oh, yeah. So the y-intercept is 0, 1, 6. If you plug that in. So we'll call that right there. How about? Okay. All right. Looks like a half on my picture, but pretend it's a 0, 1, 6. What else? What else? Who haven't I heard from? Teo, go ahead.
The vertical asymptote at x minus -2. Also what
-2 and at +3. Okay. Anything else? What are we missing? Anything else you want to say?
There's a x-intercept at
1, 0. Yeah. All right, we got that up here, but it's all good. What else, Maddie?
Is the y value of the whole at
Oh, you actually want to find the y value of the whole. All right, well, you could do that. I'm just going to throw it on there. 2, 1/3. Just like somewhere in there. Okay. All right, and then what else do we have, guys? Yeah, is there a horizontal asymptote? What is it?
How do we get that?
Y equals 0.
What?
All right, here we go. Now we're going to graph it. I think maybe it's not too much of a stretch to think that this middle part looks like this.
Oh.
Okay, we have maybe assume. We don't have to assume. We can check some other points if you like, right? But it's not a bad guess. Now, but what about this stuff over here? Because we know that it's okay to plug in values bigger than 3 or less than -2. So can we come up with what's going on down here? Let's all, for fun, plug in -3.
No.
And I actually don't care what the y value is, okay? Let's plug it into this right here. Do you see it? Into the factored form. If you plug -3 in, I just want to know, do you get something positive or negative? That's my big question. If you plug in -3, this will be, I don't actually care, it'll be what? Negative? This will be negative, 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 negative. What's a negative times a negative divided by a negative times a negative times a negative?
Negative. It's negative.
It's a negative.
Negative times a negative divided by a negative times a negative times a negative.
What just happened?
Everything's fine. All right, I want to make sure did you catch the reasoning on that? Yes. If you plug in a number less than -3, feel free to try another one. You will get something negative, always, over here, okay? What about over here?
Positive.
We'll get something positive? Try it. Because everything is
Oh,
positive.
wait. Yeah, that works.
All right, so I think without actually getting any more values, I have a fairly decent picture of what this curve looks like. And notice that this provides an excellent counterexample for those who think that you can't cross a horizontal asymptote, right? We just did, all right? Just deal, okay? I would love to be able to throw in one more example before you go, okay? because this has a slant asymptote, and I want to show you at least the beginnings of this problem. Okay. Okay. Can we just like say this goes here? We got this. So far, so good. Now I'd like to think about what the asymptote is. I'm going to pull the same kind of trick I was thinking about earlier. That's a 3. T squared goes t into t cubed, t times. What do we get? T cubed minus 9t. Am I competing with people over there? I don't know. I'll put a 0t up there just for fun. What do we get? All right, so I say this can be rewritten as, hey guys, please, as t plus 9t over t squared minus 9. All right, now why does that help us? Listen, when we see this, what does this go to as this part here as t gets large? Just this fraction over here. As t gets large, what happens to that? If we're just thinking of this function. This whole thing goes to 0, doesn't it? Out at infinity. So what does the whole function behave like out at infinity if this doesn't contribute at all? It just behaves like y equals t. Right? It's always just the thing on top here that gives you the slant asymptote, right? Whatever the quotient is. Yeah, this whole thing is just 0 out at infinity. All right? So the picture of this is going to look something like this. Bye.